Yes.
Thanks, Bruce.
Thanks very much, Greg. This is actually the very first day of the program. The program is titled Dynamics of Planetary Interiors. And the program is organized by a group called Cider, which stands for, I have to look it up because the name has changed actually, Cooperative Institute for Dynamic Earth Research. The goal or the objective of the program is to bring together senior graduate students, postdocs, and faculty to define and work at problems that are at the boundaries of what we normally consider the traditional disciplines in this field. And the thought is that this is where a lot of the interesting things are happening, and it's where a lot of the important advances are going to be made. This particular focus, I think, is going to be primarily on terrestrial kinds of planets, terrestrial types of planets, although many of the people that are going to be participating in this program are interested in the formation and dynamics of gas giants as well as extrasolar planets. I would say that the topics that we're going to be covering during this session will range from things like the internal structures of planets, their dynamics, their long-time evolution. And I would say that the emerging view in the community really is that the dynamics of planetary interiors have a large role or large play in whether or not a planet turns out to be habitable. We know, or believe at least, that the combination of plate tectonics, which is the style of tectonics that occurs on Earth, plus chemical weathering at the surface, plays a huge role in regulating climate over geological timescales. And it's also quite likely that the existence of this particular style of tectonics is also fairly important in whether or not a planet has a magnetic field. And so in this talk, what I'm going to do is give you an overview of planetary magnetic fields. And in particular, I'm going to make the case that the existence or operation of a magnetic field or a dynamo in a terrestrial planet is a difficult proposition. And I'm going to make the argument that essentially it's really all about the internal dynamics of these planets, the way in which they cool, that's really critical in terms of whether or not these planets actually will sustain magnetic fields. And so if we're looking further into the future, where we're finding extrasolar planets and asking whether or not these planets are habitable, one of the ways that we're going to be able to, at least in principle, learn about their internal dynamics is by detecting, by one means or another, whether these planets have magnetic fields. And I should actually add that if, in terms of sort of relapsing into jargon, I guess what I would hope that you guys would stop me and ask questions if things aren't clear. I sort of encourage that, and I think it would be more interesting. Who knows, the talk may go a completely different direction from what I was planning. Okay, so I thought that I would start with our own solar system, and if we look around at what we've got in the solar system, it's quite clear that the gas giants and ice giants are quite distinct from the terrestrial planets. All of the ice giants and gas giants have magnetic fields, whereas if we think about the terrestrial planets, our nearest two neighbors, Venus and Mars, do not. It's thought that Mars may have had a magnetic field early in its history, but that it failed at some point early on in time. Maybe surprisingly, Mercury has a magnetic field. So if you're keeping score, then the gas giants are 4 for 4, and the terrestrial planets are 2 for 4, at least at the present time. So if you're just simply looking at statistics, then it's even odds for whether or not a terrestrial planet will have a field. And I'm going to make the claim in this talk that the issue about whether or not a planet has a magnetic field has everything to do with the way in which those planets transport heat from the interior to the surfaces. In the cases of the gas giants, this occurs by convection in the gas envelope of these planets. That's relatively efficient. It's very easy for these planets to get their heat out, and so dynamos are almost inevitable in these bodies. In the context of terrestrial planets, they also convect. They also remove heat by convection. But that convection in the outermost rocky layer occurs by slow creeping flows. And this is much more of a bottleneck in terms of getting heat out. And it's really the key issue in terms of whether or not a planet will have a field, is how efficient that convection in that outer rocky layer actually is.
Can I ask a question?
Absolutely.
What is an ice giant?
So an ice giant, I'm thinking of Uranus and Neptune, basically. So where there's sort of much higher abundances of some of these other components besides just helium and hydrogen. So I'm thinking of the gas giants, or the giant planets, Jupiter, Saturn, Neptune, and Uranus, and they all have magnetic fields.
Could I have a terrestrial planet that's very large, like Uranus or Neptune?
There's suggestions that those terrestrial planets exist. Maybe not quite as big as that, but there are sort of thoughts that there are super Earths, or sort of 5, 6 times the size of mass of the Earth. And so they'll be very different. And whether or not those bodies have magnetic field is something that's actively and currently debated. We're not even close to being able to decide, but it doesn't stop us from debating. Let me start with the structure of a terrestrial planet, just to sort of set the scene. For our discussions. And essentially, the planet is really divided into 2 distinct layers. The outer layer is a rocky layer, which we refer to as the mantle. Silicate and oxides and other sorts of things. It's solid primarily, but it does creep under the influence of viscous or shear stresses, and so is capable of convecting at slow speeds. Inside this rocky mantle is the liquid core, or the metal core. The outer part of that core is primarily liquid iron. We know that it's a little bit less dense than pure iron by virtue of seismic observations. The transmission of sound waves through the core tell us that the composition is mostly iron, but it does have small impurities that are dissolved into it that make it a little bit less dense than pure iron. And at the very center, we have a solid iron body, which is the solid inner core. And the thought is that it is formed by gradual solidification of the core as the core gradually cools. And so it's a little interesting in a way that the core, the liquid metal core, is freezing from the center out, because this is the place where the temperature is probably the hottest in the planet, but it's just a consequence of the phase diagram of these particular materials. So if I were to plot temperature as a function of, say, radius, a typical estimate for the geotherm would increase or would decrease as a function of radius just because of the decreasing effects of pressure. Often we approximate temperatures, at least inside the convecting parts of these planets, as being adiabats or isentropes. And the melting curve, or the estimates of the melting curve for iron and iron alloys, are a little bit steeper than estimates for the geotherm. And so the point is these 2 curves will cross. On the inside, the temperature will be below the melting temperature, so we expect it to be solid. The temperature on the outside will be higher than the melting temperature, so we expect it to be liquid. And the point is that the intersection effectively defines the transition from the liquid to the solid. The other point is that as the planet gradually cools, so in other words, as convection in this rocky part can extract heat from the interior and cool down the core, we'll then lower the temperature, and we'll evolve through a series of temperature profiles which will sort of parallel this, but gradually decrease with time. And the point is that the intersection then of the melting curve with then the new temperature will gradually migrate out. And so this is constantly moving out. The inner core is gradually growing at about 1 millimeter per year or so over geological time. So in this problem, the evolution of the core, where the magnetic field is generated, is largely going to be governed by the heat flux. And this is set by convection in the mantle.
Can I just ask what's supplying the heat? Is it initial heat?
So this is in terms of, so I'm going to touch on those things. I would say that it's mostly primordial heat, but absolutely latent heat will play an important role here. In the rocky part of the mantle, there are heat-producing elements. It's not so clear whether there are heat-producing elements in iron. The thought is that most of these elements, when the silicate part and the iron part separates, and this part drains to the center and the silicate part goes to the top, that the rocky part has greater affinity for the radioactive elements, and it takes most of them with it, essentially. But you're right. We're starting with a lot of primordial heat, and over time, actually, let me just point out that we know that this intersection point is roughly 5,800 Kelvin. So the intersection of the temperature at this boundary is roughly the same temperature as the surface of the sun, the photosphere of the sun. And so the point, I guess, is, and to come back to your point, I think, is that as the heat gets drawn out, it is mostly primordial heat. It's going to cause cold, dense fluid to form at the top, which will drive convection. You're going to then solidify an inner core and grow it. There's going to be latent heat that's produced. But also some of these impurities that are dissolved into the liquid We know also from seismologies that these tend to be excluded from the iron, and so that will produce a chemical source of buoyancy. And all of these buoyancy sources will stir the core and ultimately produce the magnetic field that the Earth, or most of the terrestrial planets that have fields, are produced probably by a combination of these sources of buoyancy. So the key point in terms of thinking about whether or not a field or planet will have a magnetic field really resolve around figuring out how large is this heat flow, how fast are we actually cooling the core. And so in terms of thermal state, we have a lot of information about the Earth. So if we just draw again, so this will be the mantle, this will be the core, this will be the liquid core, this will be the solid core. We have a variety of estimates of temperature that we can use to try to construct estimates for that heat flux across the core mantle boundary. We know on the basis of lavas or melts that get erupted to the surface that we have temperatures close to the surface in the range of about 1600 K or so. And so that's a pretty decent estimate. We have a lot of estimates that are consistent with that. And we would expect that the temperature as you went into the interior would increase by virtue of the effects of pressure. And so we increase to some value. And if we continued it along an adiabat or an isentrope, we'd get to a temperature which would be about 2800 degrees or so at the bottom. So we have estimates for the melting temperature at this boundary. And we know that this is about 5800 degrees, and we can extrapolate that up along an adiabat. So that's about 5800. This is probably about 4,200 or so. And so the point is that these, at the boundaries, we have thermal boundary layers, which is normal for a convecting system where the temperature will adjust from this point down to a surface value. And in fact, most of the heat that's removed from a terrestrial planet is removed by conduction rather than the transport of melt. And similarly, at the bottom, we have a boundary layer which will allow heat to escape from the core into the base of the mantle. And so in detail, this temperature actually revolves around and then matches up to the temperature in the core. So we have a thermal boundary layer at the bottom that allows heat to be conducted into the base of the mantle, and then a boundary layer at the top that allows heat to be taken out to the surface. And if we were to sort of zoom in on this region, expect something roughly like that, we can try to make estimates of what the heat flux would be at that boundary based on these estimates of temperature. So we have a rough estimate for the temperature difference across the boundary. We can make estimates of the thickness of the boundary layer based on models for convection in a slowly creeping flow. And we have physical estimates of the properties of thermal conductivity, things like that, of high pressures and temperatures that allow us to construct an estimate for what we think the heat flux might be coming out of the core based on these temperatures. So it's going to be based on the temperature difference, the thickness of the thermal boundary layer at the bottom, estimates of what we think the thermal conductivity are. And these are fairly uncertain, but typical numbers are sort of in the range when integrated over the whole surface of the core of 5 to 15 terawatts. Now heat is being taken out of the core.
What's the typical delta?
What is the typical data?
Data.
So for
Scale.
which part of it would you like to know about? So thermal conductivity comes from a combination of experiments, high pressure experiments, diamond animal cells. And increasingly these are now done by first principle calculations, density functional theory. Estimates of the thermal boundary layer, combination of things, it's models of convection. But also we see anomalous seismic velocities in this region, which we often attribute to some sort of boundary layer.
Approximately, I want to know the scale, not exactly.
Oh, the scale. Yes, sorry. So this is probably about 7. That's probably about, 1,500, 1,200. And this is probably about 100 kilometers, 120 kilometers, something like that.
100 kilometers.
Mm-hmm.
And the entire mantle?
And same as at the top. This is probably about 100 kilometers as well. The viscosity of this is about a factor of 10 to the 10th higher than glacial ice. So it's pretty viscous, slowly convecting. Typical estimates of the velocities of flow could be on the range of, let's say, 60 millimeters per year. would be a reasonable estimate for the convective velocities. So very, very slow creeping flows in the mantle. The liquid core has a viscosity which is comparable, or maybe even less than water. So it's very, very low viscosity fluid. And so this is a bottleneck for getting the heat out, essentially. And it's the key thing that makes terrestrial planets have such a difficult time generating magnetic fields. Another question.
Bruce, so is the viscosity change and the phase change from the mantle to the liquid core enough that there's essentially no overshooting convection?
Yeah, that's right.
Is it really like two immiscible fluids?
It's like two immiscible fluids, and the position of this boundary is entirely determined by the stresses here. So the typical stresses that you get in the flows here are on the order of maybe 100 pascals, 1,000 pascals. Stresses here, particularly in the crustal regions that produce the earthquakes, can be 100 megapascals, 50 megapascals, something like that. So it's just completely different worlds. This one, inviscid fluid virtually, casually convecting by virtue of the heat that the mantle allows it to be lost. If you could take that mantle away, it would convect like nothing you could imagine. I mean, the Rayleigh number would be gigantic. Yeah.
Is there any way to tell if the thermal boundary layer lives in the mantle or in the...
Great question, actually. We don't know. So we don't know if there's a thermal boundary layer on the core side. There could be, and I'm going to come to that in just a sec. Another question?
Yeah. Why is the difference between the inner core and the liquid core is so high? It seems that...
What do you mean different in terms of...
In temperature.
Why is that temperature gradient so large?
Yeah.
Well, it's going to be partly related to things like the adiabatic gradient is going to depend on things like the actual value of temperature. So the higher the temperature, the steeper the gradient. It's also going to depend to some extent on the compressibility of materials.
Yeah, but if this liquid conducts heat so easily,
yes,
one would expect that the temperature would equilibrate.
Okay. So you're almost going where my next point is. So if I don't answer your question in 2 minutes, we'll come back to it, okay? But if the fluid is well mixed, so that in thermal equilibrium, what I mean by that is that a particle of fluid feels no need to exchange heat with its neighbor, then you'll get an adiabatic profile. And we expect, even though the fluid velocities here are probably on the order of 10 kilometers per year. So these fluid velocities compared to these are gigantic. But we expect, to first approximation, we expect this to be an adiabatic. And so I'm going to actually label that, put a subscript A there. Because this is the key issue, is for a terrestrial planet, you need a good conductor to produce a magnetic field, right? But a good conductor will also be a good thermal conductor. And just by virtue of the fact that this core is well mixed, by these sorts of fluid velocities, it will have sort of an adiabatic or close to an adiabatic profile. And in fact, there will be conduction down that adiabat. And it turns out that when you ask the question, how large is that heat flux? So this is minus K grad TA, and I'm taking the gradient of the adiabatic temperature. So there's no boundary layers. I'm not thinking about those yet. I'm just thinking about the temperature in the interior. That the numbers that come out for this are on the order of 5 to 8 terawatts. So in other words, a significant fraction of the heat the mantle takes away from the core is supplied to the boundary by conduction. Okay, so it's kind of interesting. And what happened about
convection is inefficient then. It's not carrying most of the heat then.
So convection is not carrying most of the heat, but the fluid velocities are still sufficient to produce a well-mixed state, I would argue, at those sorts of velocities. It's worse than this, actually, okay? It's worse than this because about 2 years ago, there was a group at UC London, that actually calculated new estimates for thermal conductivity, which were appropriate for the pressures and temperatures that we expect at this particular region. So roughly 4,200 K and pressures of about 136 GPa. And the estimates of the thermal conductivity went up by a factor of 2. And so these numbers are now 10 to 16 terawatts. And so now that these two heat flows are completely in the same...
It doesn't sound like it should be adiabatic once the conductive...
Hold on a sec. So I have two IOUs out right now, right? Okay, so what gives here, right? So this sounds, so you would argue, I think what you're suggesting to me is that if these values were in excess of these values, then there's no way thermal convection can be happening, and there's no way you can have a well-mixed core, basically.
Yeah, you can have convection, it's just that I don't believe that the temperature gradient will be set by the adiabatic curve.
Okay. So the point is that for a terrestrial planet, you have the problem of basically removing enough heat that's large enough to sort of exceed these kind of values so that you will actually drive thermal convection. And so the point, I guess, is that we can have two possible states, two possible styles of convection, depending on what actually takes place. Okay, so let's consider case one, where we have Q greater than QA. So now what I'm doing is I'm using large capital Qs to denote the integrated flux over the entire boundaries. So really what I'm really intending these guys is to refer to the integrals of this over the surface, these values. And so it's certainly possible that the heat flow that the mantle is taking out will exceed the values that can be conducted toward the boundary. So this is certainly a possible situation. So what you would expect in this particular case, if this is the boundary, we have a relatively large heat flux being taken out by the mantle. We have a somewhat smaller value of heat that's being supplied to the core mantle boundary by conduction through this well-mixed, I'm arguing well-mixed fluid. And so the issue there is that you'd expect some region where you would have cooling. And so in this particular case, you would expect cold fluid to develop. You would expect this to participate then in the convection. And by having that cold material sink, you will actually expect a thermal boundary layer in top of the core if this was the case. Okay? And this buoyancy then will contribute to the driving of convection in addition to the buoyancy that we get from the latent heat and the compositional effects from here. But it's also possible that that heat flow will be less. So case 2 would be Q less than QA. And this is in some ways more interesting. So we'll now have a relatively small Q. We'll have a somewhat larger QA. And so the consequence now is that we could have a situation where we're delivering more heat toward the boundary than the mantle will actually take away. And so the expectation is that this particular region will start to warm. And so there's two possibilities. One is that the combination of thermal and probably more importantly chemical buoyancy produced by inner core growth could potentially mix this fluid layer. Okay? But I would say that given the sort of amount of inertia in these flows, these are very low amounts of inertia. Does the Rossby number mean anything to you guys? Maybe not. The importance of inertia in the energy, in the momentum balance, is probably relative to the leading order terms, maybe part in 10 to the 6 or so. So inertia is very, very small. And so the likelihood of these convective flows mixing this layer back in and taking the warm fluid back down seems very unlikely. It seems more likely that you'll have convection that is isolated to the region below and that you'll just simply have a warm stratified layer that develops at the top. And so both of these possibilities exist. I would say that in the current state, I'm going to argue a little bit later that the Earth is probably marginally in this state.
And you can't probe this with P modes?
So with the kinds of temperature differences that we're talking across this layer from the modeling point of view, it's probably on the order of a few tens of degrees. And that can't be done with P modes, really. It's not detectable at that level. But there is a way of detecting it. And if I get to it, hopefully I will, that we can actually detect these with magnetic waves, essentially, that travel through a stratified layer at the top, which is quite cool. So the point, I guess, what I wanted to make is that if the planet was in this state and we had an inner core and we had chemical buoyancy driving a large part of the convection, we can still maintain a magnetic field by convection down here, we would have a stratified layer at the top, and we're in business. But if you go back in time, and the inner core is getting bigger and bigger with time, but you go back in time, there will be a period where there was no inner core. Will there be no other sources of buoyancy besides the cold fluid that will be generated at the top? And in the event that the inner core is absent and we fall into this state, then the dynamo will fail, and there will be no magnetic field. And so it's very likely that Mars, it's very likely that Venus fall into this category. And again, I'm making the argument that I think the Earth may actually be marginally in this state as well. Okay. Okay, so, but coming back now to your question about whether or not an adiabat, that's a fair question. That's a fair question. And the argument is that it's probably pretty well mixed by chemical buoyancy.
In your diagram, you wrote the words cool and warm, which is relative to the adiabat. Right? So
it's relative to the adiabat, yeah, right. So when I sort of draw these two cases, I'm going to draw this and then rub this out again. So in one case, if that's the adiabat, so if we wanted to map these two cases onto the adiabat, what I'm really talking about is a case where, in the top case, the temperature develops and we get a thermal boundary layer, or in the other case where the temperature is slightly less. So you always have heat that's coming out of the core. It's just whether or not it's more or less than what would be taken up by conduction down an adiabat. And it's a fair point. You know, how closely does this approximate an adiabat? And it's, I would argue that it's probably pretty close. I think the velocities are large enough to get a well-mixed state, but it's a fair question.
But that's really the argument you're making. It's that it's well mixed. I mean, this could be driven entirely by chemical composition issues that you were saying, and you're just mixing entropy. That's
right. That's right.
Yeah.
That's right. Yeah, I'm just talking about mixing entropy. That's right. So, but the point is, as soon as that chemical buoyancy is gone, though, this is the only game in town, and we're done. And then the dynamo must fail. And I would guarantee you that we don't have an adiabatic state. What would happen is the whole core would thermally stratify, and convection would be shut off, and the dynamo would fail. Yeah, exactly. Okay, so let me just make a couple of comments about what's required. There's no question that the field must be sustained by convection. There's just no way around this. So here's the fluid part, liquid core. Here's the solid part. The idea that you could trap some primordial magnetic field and have it slowly decaying is just not viable. If I sort of denote this distance, the radius of the core is about a little over 3 million meters, or 3,000 kilometers. The characteristic time scale for magnetic diffusion is roughly r squared for the dipole component, pi squared by the magnetic diffusivity, which is just the inverse of 1 over the permeability and the conductivity. And so if we put in representative numbers for our estimates of electrical conductivity, we get estimates here that are on the order of 25, perhaps to 50,000 years. So on geological time scales, this is a heartbeat. So if the core were to stop convecting, the magnetic field will disappear on time scales of about this. And we know from paleomagnetic evidence of magnetization at the surface, that the Earth has had a field for probably the last 3.5 billion years. So there's no evidence that at any time in Earth's history that the convection ever stopped, that the field would have disappeared. And so it has to be actively maintained to keep it going. And we know that it must be convection, and we know that in a very low viscosity fluid, one that's rapidly rotating, that the convection will be substantially affected by the effects of rotation. And the property of the convective flows that you expect would be these sort of helical convective type of columns, which are really very important in sustaining the magnetic fields. And so I wanted to just describe briefly how this works in our models, how it works in some of our theoretical ideas, and then come back at the end, hopefully, and talk about the evidence that we have for probing these states to see whether or not one of those states or the other is realistic. So a lot of the early ideas about generation of magnetic fields through helical flows goes back to the work of Gene Parker, a famous paper from 1955, where he pointed out that if you start with the magnetic field, and I have this particular magnetic field wrapping around lines of latitude, And that if it's a fairly good conductor and you have a fluid velocity, to a first approximation, you can imagine that the field goes with the flow. And so this magnetic filament will then, or field line, will then be distorted by the influence of that flow. But if I now add a helical component to it as well, so that there's a twisting as well as a rising, it will take this filament or field line and essentially twist it into a loop like that. And so the idea is that the helical flows will lift and twist the magnetic field and perhaps produce loops like this that would be associated with some electric current, which would be nominally parallel to the initial magnetic field. And so the idea is that somehow you have to get the cooperation of all of these different convective elements to produce an alignment of the magnetic field, or alignment of the magnetic field, alignment of currents that produce a large-scale circulation that would allow you to give rise to the dipole field that we see on the planet. So that's the strategy. And so we have now models, numerical models, that simulate this, that give us some insights into the way in which this process actually takes place. So if we just simply look at the dipole component specifically, the definition of the dipole moment is 1/2 integral of r cross b.
I have a question.
Yes.
But if you want to have some kind of field like that, helical field, you must have some kind of magnetic helicity from the very beginning, magnetic helicity conserved. So it must be actually from the very beginning somehow should be formed. And magnetic helicity, it is a p-odd, so it is...
It will be conserved in the case where if you're thinking about it...
Conductivity is high.
Conductivity is high, but it's not that high, right?
Okay, my question is, how do you produce magnetic helicity? Where does it come from? Because you need it for such kind of picture.
I bet we don't.
External boundary.
I bet we don't.
Huh?
You have an external boundary?
I would say that the production of the field absolutely depends on diffusivity. We can't. The way the models work is the models work by virtue of having diffusivity. So it's not a conserved quantity. Let me show you how the models work. Okay. So I guess where I was going at this is one way you can think about magnetic fields is just think about the context of what's producing a dipole field. And I'm going to try to explain how the numerical models actually produce dipole fields and link it back to this particular process. So this is the general definition. You can either show or you can look up in Jackson's book. If I want to sort of have the Z component, the axial component of the magnetic field, without any external magnetic sources beyond the core, that this can be written as 3 over 2 mu, the integral of b dot z dv. Okay? And so the point here is that if you come back to Parker's mechanism and try to imagine how this is going to work, and I'm thinking about the z-axis or the axial component being in this direction here, that when you produce a loop of field in this way, it looks like you've got a positive contribution, sort of a positive BZ component. You'll have a negative BZ component here. And it's not really so clear that you're actually going to contribute very much to the axial moment by this process. But what actually happens in the numerical models, if we take a top view of the pattern of convection, let's draw this. What I'm going to show is the vorticity of the flow. And specifically, I'm going to look at the Z component of the vorticity that comes out of these numerical models. Looking down on them, you get these convective columns that look something like this. And I should do this with the dashed. Another solid one. Okay, so let's, for the sake of argument, take these solid lines to be the positive vorticity, positive VZ component. So the circulation is basically going in this direction and basically coming back like that. And if we also have, for this particular case, this one corresponding to vertical upwelling, then I'll put a little arrow to denote that. Conversely, the neighboring pattern will have a negative VZ component for vorticity, and it'll have a flow which goes in the other direction. And so this is the pattern. So the flow here would be like this, and the flow here would be like that. Similarly, the flow here would be outward, and the flow in here would be inward. Okay. So what happens is you have these upward flows embedded in these vertical convective structures. So you're lifting the magnetic field up, say at this particular point here. And then on the margins, you can actually ask what happens to these vertical components of the magnetic field that get produced by that upwelling. Well, on this side, you'll see that these combined flows will actually sweep one of the limbs in toward the center. And the other limb, let's say this particular limb here, will then be swept out toward the outside. So the way in which this works is by essentially sweeping one sign inwards, pushing the other one to the core mantle boundary, and ultimately diffusing it out of the core and expelling it. So you have something that's very much like the Parker mechanism. You're lifting, you're twisting, but then these long extended convective patterns, these aren't rolls, but long extended convective patterns, take one of the filaments, expel it from the core, pull the other one in, and then you accumulate a strong dipole magnetic field. And this is how the numerical models work. This is how we hope that it works in the Earth, although our simulations are not sufficiently turbulent or realistic enough to know for sure whether that's actually going to be the case. So does that answer your question? Diffusion.
So you have only dipole moment, or you have actually helical helicity as well?
So certainly, the way in which we take the vertical field and convert it back into the toroidal field can occur by a variety of mechanisms. It can be differential rotation, but it can also be the same sort of convective flows that will do the conversion. So the normal way we think about this is sort of this two-length cycle, right? In the parlance of the field, I would talk about converting colloidal flow into toroidal flow. That makes sense by this so-called alpha mechanism.
Okay,
and then
so
differential rotation is
in this case, what is a typical time? So helicity is not conserved.
No, it's absolutely not. No,
so what is a typical time? So
what would you like to know? Magnetic Reynolds number, for example?
No, I want to know the typical time for the helicity formation. So just
the magnetic helicity formation.
Yeah, for typical time. So just how long does it take when this helicity is formed?
I don't know, actually.
Is it billion of years, million of
No, nothing in the core takes that long. I mean, the field completely dies away on this kind of time scale. All the advective times are happening on time scales much shorter than this.
But we have our magnetic field is actually for quite long time.
It's a very, very long time.
Just million of years, nothing is happening with our...
No, that's not true.
It's not true?
No, absolutely not. If I were to show you a plot of the amplitude of the magnetic field over 2 million years, you would say, wow, look at all that variability. In fact, you would even find that there were at least 2 or 3 reversals during that period. So absolutely not. No, this is the long time scale. You can get an advective time scale by looking at sort of these numbers. The magnetic Reynolds number is on the order of maybe 500. It's very modest. And so the numerical models, the way that they work, and probably the way that it works in the Earth, is it absolutely relies on diffusion to expel field lines from the core to accumulate one particular sign. There's no question about that.
So the typical time scale here is just...
advective time scales. 1,000 years, sure.
1,000 years.
Yeah. Yeah. So the reversals, the last one was about 780,000 years ago was the last reversal. Okay, so if I've got time just to sort of briefly discuss...
Do people understand how this reversal works?
No, I guess we don't.
People don't? Or
well,
they do?
But the models reverse, and the models reverse essentially by growing a patch of reversed field. The point is, and I'm sure you must know, that in the induction equation, if I change the sign of the magnetic field, right, in the equation, nothing changes. In a numerical model, I change the sign.
I understand that helicity must change the sign.
Of course it does. And so what happens is that you get a perturbation in the production of field in some patch of the core. And then that essentially spreads almost like a phase transition. So there's sort of, but we don't know for sure. We don't know for sure. Okay, well, let me just finish up briefly. I'll finish up on this panel, perhaps, with observations, just to come back. How do we actually make progress, or how do we actually test any of these ideas? Okay, so early explorers like Francis Drake, James Cook, all of these guys carried with them magnetic compasses, and they measured the orientation of the magnetic field about a vertical axis, and they also measured the orientation of the magnetic field about a horizontal axis. And so there have been, over the last 400 years, these mariners have been collecting observations that allow us to reconstruct estimates of the radial component of the B field and the time derivative of the magnetic field over this extraordinarily long time scale. Maybe to put this into sort of context, if you think about the dynamics of the core, it is a rapidly rotating fluid. It's a lot like the atmosphere. Roughly 60 days in the core is comparable to a day in the atmosphere. So this isn't a lot of information. 400 years isn't a lot of information, but it's the best that we can do. But it's remarkable that we have a record that even goes back that far. And so the point is that if you looked at the evolution of the radial component of the magnetic field at the top of the core, where the radial velocity has to vanish, then it obeys an equation written as follows. So we have the advective term. I'm looking at the horizontal gradient operator. The velocity is purely horizontal in this particular case. And we have a diffusion term here, which involves the magnetic diffusivity. I think I've got this right. And so the argument is for over time scales of, say, a few hundred years, short time scales, advective time scales, that we can neglect this part. But I'm still claiming it's absolutely essential down here, right? And the point is that it allows us to relate. So if we have estimates of the rate of change of the magnetic field, and we know what the magnetic field is, then in potential we can invert this equation and get estimates of the fluid velocities that produce the change.
So the mantle is sufficiently...
So the mantle is sufficiently, yeah, that's a great point, thanks. The mantle is really a very good insulator. And so the usual assumption is that you can take field observations at the surface and downward continue them through a vacuum, basically, to the surface. And that's a pretty good assumption. Typical conductivities are probably on the order of 1 to 10 Siemens per meter. Don't know that order. Pretty low. So there's a problem with this equation, perhaps in the sense that you have one equation and you're trying to back out two unknowns, sort of the east and the north components of the velocity, so it's non-unique. But you can add dynamical constraints to the equation, saying what you think the relevant force balance is, to provide enough additional constraints to invert reliably, not uniquely, for the fluid velocities. And the inference that has come out from these observations is that the flow basically has a steady component, probably reflects the sort of the slowly evolving convective pattern in the deep interior. And it also has an unsteady component. And I'm going to call this a wave because there's a dominant periodicity associated with this that's roughly on the order of 60 years. There are others, but there's a dominant periodicity of about 60 years. And so people have been thinking about this for a long time and have tried to work out ideas for what might be the origin of these waves that we're detecting in the core. One of the original thoughts by Berkeley was that these were a type of magnetic wave. If you just look at a section of the core, you're looking at flows which have periods, wave-like motions, which have periods of about 60 years. These are rotationally dominated flows. These are going to be nearly geostrophic, which means that there's a very close balance between the pressure gradients and the Coriolis force. And in a deep fluid like the core, the only possible geostrophic flow is one that is purely following lines of latitude, essentially. And the other consequence of rapidly rotating flows, so-called Proudman-Taylor theorem, tells us that there are no variations in that flow in the direction of the rotation axis. So if this is the direction of the rotation axis, we can only have flows that follow lines of latitude. And what's more is that the fluid velocity has to be the same on that whole sheet. So these flows are organized in the form of cylinders. Now we can have a flow in a different direction at a different radius, so perhaps a flow at this particular point can be moving in this particular direction. It will also be constant along the cylinder. And the idea is that you have a line of field that extends through these cylinders. Then in principle, as these cylinders differentially rotate, they will stretch the magnetic field. That will produce a restoring force. It will produce waves. And to produce the periods that we actually see in these observations, periods on the order of 60 years, we need magnetic fields that are on the order of 2 to 3 milliteslas.
Sorry, what's the nature of the magnetic wave again?
So the nature of the magnetic wave, imagine, so these think of those filaments as almost like elastics, right? And so you're differentially rotating, there's a sort of a tension, and then that tension restores. So the fluid motions are basically the motions of these cylinders.
So they're
back and forth.
alphanic?
They're alphanic waves, yes.
Magnetic torsional wave?
It's torsional oscillations. It absolutely is, yes. It absolutely is. And to get the periods about right, you need these field strengths are in this sort of order. The numerical models suggest that the field strengths are perhaps a factor of 10 bigger. And so this idea has fallen out of favor. So another possibility, and this is the last thing that I'll show, is that there's another way that we can get these waves to work. It's possible to have a different type of wave, a wave known as a Mach wave. It involves a three-way balance between magnetic forces, buoyancy effects, or Archimedes effects, and Coriolis effects. And it involves the situation where we have a stratified layer at the top of the core. And so the idea here with these waves that we've got some layer which has some, say, thickness, which we'll denote by H. We'll characterize the strength of the stratification by the buoyancy frequency, which depends on what the radial gradient in density is. So minus G over rho, partial R. And with this configuration, it's possible to get waves that will propagate in the stratified layer and have periods that are compatible with the 60-year periods that we see in the observations. The way that these things work is that if I have a radial motion here, let's say, I'm bringing less dense fluid downward, so I'm producing a negative density variation, okay, which will produce a low pressure in this particular part of the stratified layer. Similarly here, if I have upwelling at the equator, then that will produce a positive density anomaly. And so these flows will be very much like the flows that you get in the atmosphere. You would get sort of a geostrophic flow around these pressure lows, would give rise to flows which have that same sort of structure, the same sort of pattern at the surface, at least, as we infer from these torsional oscillations. In addition to this, because there's a magnetic field that threads across this layer, as that zonal flow will stretch that magnetic field line, it will produce some friction, and that will induce what is effectively an Ekman pumping, which produces a flow which will travel in this direction, a much more modest flow that goes in that direction. And so the waves that will be set up can actually have periods which are about the right periods. And so what you can do is you can actually look at these flows, look at these waves, and ask the question whether or not those flows are compatible with the flows that we recover from these magnetic field observations. And the answer is we can do a very good job reproducing those flows if the thickness of this layer, H, is roughly on the order of about 140 kilometers thick, be about 5% of the thickness of the core. And if the buoyancy frequency is roughly on the order of the rotation rate. And we'll get periods with rightfully the right period that have roughly the right spatial structure. And the last piece of information, which for me at least was actually very compelling, is that this weak meridional flow, this flow toward the pole, will also produce variations in the dipole field. In effect, what's happening is that meridional flow will sweep field lines toward the pole, which will produce a stronger dipole field, and then conversely spread the field away from the pole and produce a fluctuation. So we would expect fluctuations in the dipole to be compatible with this story, and the answer is that that is compatible. So I think we have pretty good evidence based on these Mach waves, or evidence for Mach waves, that in fact the core does sit in this particular state. And maybe just to simply wrap up, I'll just say we can estimate some of these parameters that we require to produce a layer which is about 140 kilometers thick, and look at what the buoyancy frequency is. And so for a Q of roughly on the order of 13 terawatts, we can get a layer which has the right thickness if the adiabatic heat flux is about 15 terawatts. And you can make predictions about what the buoyancy frequencies would be in these layers just simply based on the thermal structure of these layers, right? And we get frequencies, buoyancy frequencies, that would arise from this would be about 1.5 omega. So in the right order of magnitude that we need to explain the value that we're recovering from these field observations. So the point, I guess, is that in summary, terrestrial planets operate in this state where they have a bottleneck of this rocky mantle that prohibits or limits at least the amount of heat that can escape. And that value is critical for deciding which of these two states the core is going to be in. If it falls very deeply into this state, the dynamo will fail. And we have evidence based on waves and observations of magnetic field variations that the Earth probably marginally sits in that state. And so these planets sitting on the edge make them very useful diagnostics, I think, of the internal dynamics of terrestrial planets. And so to come back again to the exosolar planet story, if we're looking into space and we can detect evidence of magnetic fields, then we have the opportunity to learn an awful lot about the internal dynamics from observations in principle that we can make from space. Thanks very much.
Questions?
I'm happy to take more questions.
So this maritime data is consistent with an axisymmetric way, basically, as you described.
Yeah,
it's just increasing and decreasing the dipole.
That's right. So I guess I have to say that these flows, of course, a lot of the evidence for these zonal flows come from the non-zonal part of the magnetic field. Because the way, if you conceptually imagine it, what you're really doing is you're identifying a patch of flux, and then you're seeing that patch of flux get swept this way, and then you're seeing that patch of flux get swept back the other way. And so what goes into the construction of these zonal flows is really time variations in the non-zonal part of the field. And so if you were to try to sort of match the flows that you get from those variations, you get these sorts of properties. But it's just very encouraging that when you take these flows that have been fit to those non-zonal observations, they make predictions for what the dipole should do. And they're compatible with those observations. And so they're both field observations, but in many ways they're quite independent because of the different sorts of information that go into the flows of Birch's. So a dipole variation would not require, this kind of flow would produce no variation in the dipole. It's really only this.
Right.
And you only get this when you have a wave. If you have a purely geostrophic flow, you don't have that component. And so to me, at least anyway, is that this story actually provides, I think, a lot of support for the existence that the Earth, in fact, might be in this state.
How could you measure magnetic fields of extrasolar planets?
Yeah, that's a good question. So that's for the clever astronomers, right? So you could imagine synchrotron radiation, for example, coming off of a planet, for example.
For very, very close-in ones, you can sometimes see interactions between the planet and the star. That's largely for gas giants that are very, very close.
You can see that. And what do they actually detect, though? What are they measuring?
They see increased activity on the star that correlates with the planet's orbit.
Okay. Because I've seen arguments for the idea that the magnetic fields and interactions could produce ohmic heating, which could inflate some of these gas giants, right? That they could give them sizes that are incompatible with what you'd expect from thermal evolution models. But again, the point I suppose is that to do the internal geology and dynamics of these planets, the only way that I'm aware that you can do it at all would be by virtue of magnetic fields. And so at least in principle, it is possible to detect from space. How you precisely do that, of course, is a challenge.
What's the typical magnetic field for all these planets?
Depends, right? The Earth's
compare with magnetic field on Earth.
So the Earth's field is something on the order of sort of probably 20 to 30 milliteslas. We expect for planets, Jupiter and Saturn, the planets' fields are probably maybe an order of magnitude higher than that.
Higher than that.
I mean, normally the way that these things get scaled is in terms of the convective heat flux, the buoyancy flux. Is usually a pretty good parameter for trying to scale these things. And though heat fluxes in those planets are much higher than for Earth, for example. So the fields are much stronger. Yeah?
Can I ask you to focus a little bit on the terrestrial planets in our solar system?
Okay.
So how should I think about the other terrestrial planets?
So I think that's also a great question. So I think in the context of Venus, for example, Earth has plate tectonics. And what that means is that these cold boundary layers at the very top actually get recycled into the interior. That whole cold boundary layer gets pushed back and you bring new material up. That's very efficient at getting heat out of the planet. So a planet that operates with plate tectonics is liable to have a much higher heat flow at the core mantle boundary than a planet that has a rigid static layer at the top, which doesn't participate in the convection, which is what we think Venus does.
So Venus has had this.
So Venus probably has had this problem forever. Yeah, and so It's probably have a heat flow. Estimates would suggest that the heat flow at the core mantle boundary of Venus might be a factor of 10 lower. And so it's just way too low to be even close to viable. And so it probably has never had a magnetic field, with maybe the possible exception of a very vigorous early first phase. Mars is probably the same. That Mars may have had sufficient geological activity to get the heat flows here large enough to produce a magnetic field early on. But then as it gradually cooled, that heat flow dropped and it fell below the critical. And it probably was in a regime where it wasn't hot enough and the pressure wasn't high enough to solidify a solid inner core. And so it also. The one that surprises me the most is Mercury, because Mercury has a very thin silicate shell, but it's probably not convecting. At least people think it might not be convecting. How Mercury has figured out how to get the heat out to make this work is not clear. That's a surprise. And then you can turn to planets or satellites like Ganymede, for example. How does that work? And again, that's another challenge. And for some of these bodies, increasingly people are beginning to think that tidal effects might be important. So the way that you pump the energy in is not by convection, but by mechanically doing things with the boundary. And that's all another class of problems that we don't think are relevant for the major terrestrial planets, but may be relevant and appropriate for small satellites.
Is the rotation rate important?
So rotation rate is only important in the sense that you need to get into a regime where the style of convection gives you the helical flows that you need to produce the magnetic field generation. So Venus, for example, the relevant magnetic number is the magnetic, or not the magnetic, it's the Rossby number. And for Earth, that Rossby number is about 10 to the minus 6. It's small. And you want it small to get these sorts of flows. For Venus, it's rotating maybe 100 times slower. So maybe the Rossby number is 10 to the minus 4. So it's still small. So I would say if Venus, even with its slow rotation, had a sufficiently active system of mantle convection going on that could raise the heat flow large enough to get it to convect in the core, I think it would have a magnetic field. And so I think rotation probably isn't the key parameter in that particular question. Yeah.
And for Venus, how do you know that there is no magnetic field? With what precision? So it's 10, 100, 1,000 times smaller
Yeah,
than
right. So
Earth
there's
magnetic
probably,
field?
you're right. So there's probably a limit on the strength that the magnetic field
So
can be
what
on.
is the upper limit?
Yeah, I'm not sure.
To the -3, I think it
Is that right?
-3 from Earth's magnetic
Yeah.
field. And the same for
Mars.
Mars.
I mean, most of Mars's field today is remnant, actually. Most of the field that we see on Mars is field that's frozen into the crust of the planet from a time when it used to have a magnetic field, and those rocks were magnetized by that magnetic field. And it doesn't have a coherent large-scale magnetic field anymore.
So you can measure coherent length scale as well?
Well, you can definitely,
entire
yeah, with satellite missions that have gone to Mars, yeah, we have very good estimates of magnetic field on Mercury, or Mars rather. Yeah.
So you can measure correlation lengths for
Yes.
entire planet?
Yes. Yeah. What you see, for example, in the dating of when it failed is largely based on impact craters. What you find is that an impact crater that was formed early on that produced melt, when it solidified and cooled, will possess some magnetization. And impacts that happened later in geological history that cool when there was no magnetic field are unmagnetized in the present-day Mars. And so we have a rough idea that it was probably about 4 billion years ago, maybe a little bit later, that the field shut off on Mars. And it was probably just simply a question of running down, the planet's a little bit smaller, its time scale for cooling would be a little bit more rapid, a little bit shorter, and so it's evolved out of a state where it could sustain a magnetic field early on in its history.
So is this the main focus of this program, by the way?
So the main focus of this program would be thinking about the dynamics of the planet as a whole. So it will involve aspects of the tectonics, it will involve aspects of the mantle dynamics, it will involve aspects of the field generation that goes on inside. It's going to involve people that will be providing estimates of material properties like thermal conductivity, for example, at very high pressures and temperatures. It will involve seismologists, for example, that provide detailed structures of the internal parts and tell us, how much less dense than pure iron is this, and how much light element do we need to dissolve in that, and how much chemical buoyancy do we have to produce this. And it will also involve some people that are geochemists, because one of the lasting legacies of planetary evolution is it leaves behind chemical signatures, which geochemists can interpret and try to incorporate into this framework to try to imagine, here's the planet that we see today, what is the evidence of the planet that has existed in past times. So the geochemistry, the mineral physics, material properties, the dynamics, and seismology are sort of all parts that will come together to attack the planet as a whole dynamical being, essentially. Okay.
One more question, sir.
Okay, sure.
So you argue that actually the typical scale for changing helicity is 1,000 years.
That's the convective time scale. I would
Okay.
say that's probably right, yes.
1,000 years. And at the same time, I understand that the changing of the just on Earth, million of years.
The reversals.
The
reversals is
the
millions of
direction.
years, yes.
And my understanding that the way how a reversal can work, you change the helicity. So if typical time scale for the helicity changes 1,000 years, how you can argue that actually a reversal time scale could be million of years?
Well, the reversals,
because it is one and the same.
Well, the reversal time, so that the time scale that it goes from one stable state to the other stable state is on the order of a few thousand years. And then it stays in that stable state for a very long period of time, right? And you know that the magnetic induction equations permit both states equally well, right? If there's no
heterogeneous, there is no sign.
There's no sign. That's like right. So the fact that the reversal is happening on timescales of thousands of years is the timescale that is required to reverse the field. But then once it's in that structure, it can persist for a very long period of time. And the issue really is, what are the amplitudes of the perturbations? When do they become large enough? And how often do those perturbations occur that are large enough to kick you into a different state? The way I kind of picture it is sort of this bistable potential well. And that you're sort of sitting in one state. If you get a large enough perturbation, you can hop over that threshold and move into the other state. And so what we're talking about with reversal rates or periods is what's the probability of a perturbation that will be large enough to knock you into the other state.
So like in quantum mechanics, tunneling between one state and another state, which have the same energies.
Right. We don't think that process happens.
For sure,
but I
it's
don't.
not tunneling, but the way how you describe it looks
yes,
like that.
Yes. Okay. Well, we'll bring that up. I don't think that's going to get much traction.
Everyone has to go back and read Sidney Coleman's.
That's right.
papers
That's right.
now.
Exactly right. Thanks very much.
Okay. Thank you.